There is a moment that every astronomer dreads. The moment when the data arrives, the images resolve, the spectra unfold across the screen, and nothing makes sense. The James Webb Space Telescope was built to answer questions. It was engineered with 17 years of labor, $10 billion of investment, and the focused ambition of 3 space agencies. Its golden mirror, 6.5 meters across, was designed to capture the faintest whispers of light from the edge of observable reality. Its instruments were calibrated to dissect that light into information, to translate photons into understanding. The telescope works. It works better than anyone hoped. The images are sharper than specifications promised. The spectra are cleaner than engineers predicted. The data flows back to Earth in a steady stream of discovery. And yet, something is wrong. Not with the telescope, with the universe. Object after object, observation after observation, Webb reveals things that should not be there, structures that formed too quickly, chemistries that evolved too early, patterns that our models cannot reproduce. The telescope was sent to confirm our understanding of cosmic history. Instead, it has quietly, systematically, devastatingly undermined it. This is not the story of what James Webb discovered. That story has been told in press releases and popular articles, celebrated with stunning images and triumphant headlines. This is the story of what James Webb did not tell us. The silences between the discoveries, the questions that multiply faster than answers, the growing suspicion that our picture of the universe is not merely incomplete, but wrong in ways we are only beginning to recognize. Let us begin with something fundamental. Temperature. The universe has a temperature. It is not uniform, not exactly, but it is remarkably close. The cosmic microwave background, that faint radiation left over from the era when atoms first formed, glows at 2.725 Kelvin in every direction. The variations are tiny, measured in millionths of a degree. This uniformity is often celebrated as confirmation of our cosmological models. But it contains a problem that has never been fully resolved. For the universe to have such uniform temperature, different regions must have exchanged energy at some point in the past. They must have been in thermal contact, sharing heat until they reached equilibrium. This is how temperature becomes uniform anywhere, from a cup of coffee cooling to room temperature to a gas expanding to fill a container. But here's the difficulty. Regions on opposite sides of the observable universe are so far apart that light has not had time to travel between them since the Big Bang. They have never been in causal contact. No signal, no energy, no information could have passed from one to the other. How did they reach the same temperature? The standard answer invokes inflation, a hypothetical period of exponential expansion in the first fraction of a second after the Big Bang. During inflation, the theory goes, a tiny region that had already reached thermal equilibrium was stretched to cosmic scales. The uniformity we observe is a fossil of that early equilibrium, preserved across distances that later became causally disconnected. Inflation is elegant. It solves multiple problems simultaneously, but it is not observed directly. It is inferred from its consequences, and those consequences depend on specific assumptions about how inflation occurred. Webb cannot observe the inflationary epoch. No telescope can. But Webb can observe the structures that grew from the post-inflationary universe, the galaxies and clusters and cosmic web that emerged from the tiny fluctuations inflation left behind. and some of those structures do not match inflationary predictions cleanly. The distribution of matter on the largest scales should follow specific statistical patterns if inflation occurred as our simplest models assume. These patterns have names: the scalar spectral index, the tensor-to-scalar ratio, the non-Gaussianity parameters. They have been measured with increasing precision over decades. Most measurements match predictions, but not all. There are features in the cosmic microwave background at large angular scales that standard inflation does not explain. A hemispherical asymmetry, where one half of the sky shows slightly different fluctuation statistics than the other. A cold spot larger and colder than random fluctuations should produce. Alignments between the largest scale patterns and the geometry of our solar system that should be coincidental but persist stubbornly through increasingly sensitive measurements. Webb's contribution is indirect but important. By observing how matter clustered in the early universe, by tracing the growth of structure from high redshift to low, Webb tests whether the fluctuations behaved as inflation predicts across cosmic time. The results are not definitive, but they add to a pattern of mild tensions, small discrepancies that individually might be dismissed as statistical flukes, but collectively suggest something is not quite right with our simplest models. The temperature uniformity problem has a cousin, the flatness problem. The geometry of space can be curved, like the surface of a sphere, or flat, like an infinite plane. General relativity allows for both possibilities, and the curvature depends on the total energy density of the universe compared to a critical threshold. Observations show that space is flat to extraordinary precision. The curvature, if any, is too small to measure. This seems like a simple fact, but it requires explanation. In an expanding universe, flatness is unstable. If the universe began with even a tiny deviation from perfect flatness, that deviation would grow over time. By now, after 13.8 billion years of expansion, any initial curvature should have been amplified to easily detectable levels. The fact that we measure flatness means the initial conditions were tuned with extraordinary precision. The universe started almost exactly flat, to many decimal places, for no apparent reason. Inflation solves this too. The exponential expansion during inflation drives the universe toward flatness regardless of initial conditions, like inflating a balloon until its surface appears flat. Any initial curvature is stretched to insignificance, but inflation requires its own fine-tuning. The field that drove inflation must have had specific properties. Its potential energy must have taken specific forms. The physics that ended inflation and produced the fluctuations we observe must have operated in specific ways. We have traded one fine-tuning for another. The flatness problem is solved, but the inflation problem remains. Webb cannot directly probe these foundational questions, but it constrains them by mapping the universe that emerged from these early conditions. Every observation of galaxy clustering, of cosmic structure, of matter distribution, tests whether the inflationary paradigm holds. So far, the paradigm holds approximately. But approximately is not the same as perfectly. And the deviations, small as they are, point toward physics we do not understand. Let us move from the earliest moments to the cosmic structures that emerged from them. The universe is not uniformly filled with matter. It is structured, organized into a vast network of filaments and nodes called the cosmic web. Galaxies cluster along these filaments, gathering at the intersections to form massive clusters. Between the filaments lie voids, enormous empty regions where almost nothing resides. This structure is not random. It is the gravitational amplification of quantum fluctuations from the inflationary epoch, grown over billions of years into the pattern we observe today. The cosmic web is one of the great confirmations of cosmological theory. Simulations based on our standard model produce webs that resemble the observed structure in remarkable detail. The filaments form where they should. The voids grow as predicted. The statistics of clustering match observations. But the match is not perfect. Webb has contributed to mapping the cosmic web at higher redshifts than previously possible, tracing its evolution across cosmic time. These observations reveal a web that matured quickly, perhaps too quickly, at redshifts corresponding to just 1 to 2 billion years after the Big Bang. The cosmic web already shows surprising organization. Filaments are well defined. Protoclusters are already assembling. The structure has developed further than simulations typically produce by that epoch. This is part of a broader pattern. Galaxies, clusters, the cosmic web itself, all seem to have formed and organized faster than our models predict. The early universe was not the chaotic, primitive place we expected. It was already structured, already complex, already old, in a sense that our physics struggles to explain. One possibility is that dark matter behaves differently than we assume. The standard model treats dark matter as cold and collisionless, particles that interact only through gravity, with negligible velocities compared to light. This cold, dark matter clusters efficiently, pulling ordinary matter along with it. But what if dark matter is not purely cold? What if it has properties, self-interactions, or thermal velocities, or connections to other fields that modify how it clusters? Different dark matter physics would produce different cosmic web evolution. Perhaps the rapid early structure reflects dark matter we do not understand. Another possibility involves dark energy. We model dark energy as a cosmological constant, a fixed energy density that does not change as space expands. But dark energy could evolve. It could have been stronger or weaker in the early universe. Different dark energy histories would affect how structure grew, potentially explaining the rapid early development. Webb cannot directly detect dark matter or dark energy, but it can observe their effects, traced through the distribution and motion of visible matter. Every galaxy Webb observes is a test of our dark sector models, and the tests, while not failing outright, show hints of inconsistency. Let us consider the objects that populate the cosmic web, the galaxies. Galaxies are not simple objects. They are systems of hundreds of billions of stars, bound together by dark matter, filled with gas and dust, shaped by magnetic fields and radiation and gravity. They form, evolve, interact, merge, and die through processes that span billions of years. Our models of galaxy formation are sophisticated. They track dark matter halos as they assemble through hierarchical merging. They follow gas as it cools and condenses to form stars. They include feedback from supernovae and supermassive black holes, which can heat or expel gas and regulate star formation. They produce simulated galaxies that resemble observed ones in many respects. But Webb has found galaxies that these models cannot easily produce. Consider the issue of morphology. Galaxies come in shapes: spirals with rotating disks and prominent arms, ellipticals with smooth, featureless profiles, irregulars with chaotic structures. These shapes reflect formation histories. Spirals form from gas that settled into rotating disks. Ellipticals often result from violent mergers that scrambled ordered motion. In the early universe, mergers were frequent. Galaxies were closer together, collisions common. Simulations predict that early galaxies should be disturbed, chaotic, showing the scars of recent interactions. Webb has found the opposite. At redshifts exceeding 3, corresponding to when the universe was less than 2 billion years old, Webb has observed disk galaxies with smooth, regular structures, spiral patterns already in place, rotation curves showing ordered motion, morphologies that would not be out of place in the present-day universe. How did these disks survive the violent early universe? How did they form so quickly and remain so undisturbed? One possibility is that cold gas flows along cosmic web filaments directly into forming galaxies. These flows could deliver angular momentum efficiently, building disks rapidly without requiring violent mergers. The disks would form smooth and stay smooth because the gas supply is continuous and orderly. But this explanation has problems. The simulated cold flows do not always produce the observed disk properties. The angular momentum delivery is not always efficient enough. The observed disks are sometimes too massive, too settled, too mature for any model to comfortably explain. Another possibility is that our understanding of stellar feedback is incomplete. Supernovae and stellar winds inject energy into galactic gas, driving turbulence and outflows. If feedback operates differently than models assume, perhaps more gently, perhaps more directionally, it could allow disks to form and survive where current simulations disrupt them. But adjusting feedback to save the disks often creates other problems. Too little feedback produces galaxies that are too massive, too star-forming, too unlike what we observe in other respects. The parameters that fix one problem often break another. Webb has revealed the disk galaxies. It cannot tell us how they formed. The disk puzzle connects to a deeper question about galaxy evolution. How do galaxies regulate themselves? A galaxy is not static. Stars form from gas. Stars die and return processed gas to the interstellar medium. Gas flows in from the surrounding circumgalactic medium. Gas flows out, driven by supernova, stellar winds, and the energy released by accreting supermassive black holes. These processes are called the baryon cycle, and they determine how galaxies grow and evolve. If gas flows in faster than it flows out, or forms stars, the galaxy accumulates fuel and builds stellar mass. If outflows dominate, the galaxy starves and star formation slows. The baryon cycle should leave observable signatures. Outflowing gas should produce blue-shifted absorption features in galactic spectra. Inflowing gas should produce red-shifted features. The circumgalactic medium around galaxies should show specific temperature and density profiles, reflecting the balance of processes. Webb has observed these signatures with unprecedented clarity, using its infrared spectrographs to probe the gas around and within galaxies across cosmic time. The observations are puzzling. Some galaxies show outflows where models predict inflows. Others show the opposite. The velocities of gas motions do not always match the predictions based on galactic properties. The circumgalactic medium seems more complex, more structured, more variable than simulations produce. What this means is not clear. Perhaps the models are missing physics that becomes important under conditions Webb observes. Perhaps the observations are sampling unusual systems, not representative of the broader population. Perhaps the baryon cycle operates differently, in different environments or at different epochs. Webb has provided data. Interpretation lags behind. Let us turn from gas to stars, to the populations of stars within galaxies and what they reveal about cosmic history. When stars form, they span a range of masses. The distribution of these masses, the initial mass function, determines how a stellar population evolves. Massive stars burn bright and die young, enriching their surroundings with heavy elements. Low-mass stars burn dim and live long, accumulating over cosmic time. For decades, astronomers assumed the initial mass function was universal. Stars forming anywhere, at any time, followed the same mass distribution. This simplification enabled calculations of galaxy properties from integrated light. If you knew the star formation rate and assumed the mass function, you could predict the galaxy's brightness, color, and chemical evolution. Webb's observations have challenged this assumption. In certain environments, particularly in the early universe and in extremely dense star-forming regions, the mass function appears to differ. There seem to be more massive stars than the standard function predicts, a top-heavy distribution that would change everything downstream. If massive stars were more common in the early universe, those galaxies would have been brighter than we estimate. Their chemical enrichment would have proceeded faster. Their ionizing radiation would have been more intense. The ionization of the universe, when ultraviolet light from early sources ionized the intergalactic hydrogen, would have happened differently. The evidence for a variable mass function is not yet definitive. Measuring the mass function in distant galaxies is indirect and uncertain. Webb sees integrated light, not individual stars, and inferring the mass distribution from that light requires assumptions that may not hold. But the hints persist across multiple observations, multiple analysis methods, multiple research groups. Something about star formation in extreme environments seems to produce more massive stars than our local neighborhood does. This would have profound implications. The chemical evolution of the universe, the history of element production from the Big Bang to now, depends on which stars formed when. If the earliest stars were systematically more massive, the first heavy elements appeared earlier, in different proportions, through different pathways. Webb has observed the chemical compositions of early galaxies through their emission and absorption spectra. These observations test whether the enrichment patterns match models based on standard star formation. The patterns are complex. Some elements appear in expected proportions, others do not. The ratio of nitrogen to oxygen varies in ways that standard nucleosynthesis does not explain. The ratio of carbon to iron shows scatter beyond what models predict. The early universe was chemically heterogeneous in ways that require explanation. One possibility is that the first stars were indeed more massive, producing element ratios that differ from present-day stellar yields. But pinning down the mass function from chemical abundances requires knowing how elements were mixed and transported through the early universe, processes that are themselves poorly understood. Another possibility involves our process nucleosynthesis, the rapid neutron capture that produces the heaviest elements. If our process sites were more common or more productive in the early universe, they would have altered the abundance patterns in ways that could explain some observations. But identifying our process contributions is difficult, and the sites themselves, whether supernovae or neutron star mergers or something else, remain debated. Webb has revealed the chemical complexity. Explaining it requires understanding stellar evolution, nuclear physics, and galactic dynamics in ways we have not yet achieved. The stars hold another puzzle. Some of them refuse to die properly. When a massive star exhausts its nuclear fuel, its core collapses. In most cases, this collapse produces a supernova explosion, one of the most energetic events in the universe. The outer layers of the star are ejected into space, enriching the interstellar medium with newly synthesized elements. What remains is a compact remnant, a neutron star, or, for the most massive progenitors, a black hole. But theory predicts that some massive stars should collapse without explosion. If the infalling material forms a black hole before the shockwave can escape, the supernova fails. The star simply vanishes, its light fading as the black hole swallows everything. These failed supernovae should be detectable through monitoring programs that watch for disappearing stars. A few candidates have been found in nearby galaxies, stars that were present in earlier images, but absent in later ones, without corresponding supernova detections. Webb has observed some of these candidate failed supernovae, using its infrared sensitivity to search for any residual emission at the star's former locations. The results are ambiguous. In some cases, Webb confirms the disappearance. No infrared source remains. Whatever happened to the star left nothing detectable behind. In other cases, Webb finds faint infrared emission where the star once was. This emission could come from dust, heated by the collapse event, from a surviving stellar remnant, or from something else entirely. The nature of the emission is unclear. If failed supernovae are common, they would affect our understanding of cosmic chemical enrichment. The heavy elements synthesized in stellar cores would be swallowed rather than dispersed. The overall metal production of the universe would be lower than models based on successful supernovae predict. They would also affect the black hole mass distribution. Failed supernovae might produce heavier black holes than typical core collapse supernovae, since more of the stellar mass falls into the black hole rather than being ejected. Webb cannot determine how common failed supernovae are. It can only study individual candidates, constraining their properties one by one. The broader statistical picture remains uncertain. Let us shift from stellar death to something between stars and planets, to objects that blur the boundary between these categories. Brown dwarfs are objects too massive to be planets, but too small to sustain hydrogen fusion in their cores. They occupy the mass range between roughly 13 and 80 Jupiter masses, glowing faintly with heat left over from their formation, gradually cooling over cosmic time. The coldest brown dwarfs, called white dwarfs, have surface temperatures comparable to a warm oven, or even room temperature. Their spectra show features from molecules like ammonia, methane, and water, signatures more reminiscent of planetary atmospheres than stellar surfaces. Webb has observed white dwarfs with sensitivity that reveals details invisible to previous telescopes, and their atmospheres are strange. Models of brown dwarf atmospheres predict specific temperature profiles, chemical compositions, and cloud structures based on physical principles. These models work reasonably well for warmer brown dwarfs, where observations and predictions agree. But for the coldest white dwarfs, the models fail. Spectral features appear at unexpected strengths. Chemical species are present in abundances that equilibrium chemistry cannot explain. The inferred temperature profiles have inversions and gradients that do not match calculations. What is happening in these frigid atmospheres? One possibility is that vertical mixing is more vigorous than models assume. Convection could dredge material from deep layers where chemistry differs, producing the unexpected compositions observed at the surface. Another possibility involves cloud physics. Clouds of water, ammonia, or more exotic condensates could form at altitudes where models predict clear skies, modifying the spectra in ways standard calculations miss. A third possibility is that our fundamental understanding of atmospheric physics breaks down under the conditions in white dwarfs. Their gravities are higher than Jupiter's. Their temperatures span unusual ranges. The physics might simply be different from what we encounter in more familiar objects. Webb has revealed the atmospheric puzzles. Atmospheric modelers are working to resolve them, but progress is slow. There is another aspect of brown dwarfs that Webb has probed. The boundary between brown dwarfs and planets is defined by mass, with 13 Jupiter masses as the dividing line. But mass is difficult to measure directly for isolated objects. Webb has found objects in young star-forming regions that might be either very low-mass brown dwarfs or free-floating planets ejected from their birth systems. The distinction matters because it speaks to formation mechanisms. Brown dwarfs form like stars from collapsing gas clouds. Planets form in disks around stars. The two pathways are physically distinct, but Webb cannot always tell which pathway produced a given object. The boundary between brown dwarfs and planets may be fuzzier than our definitions suggest. From brown dwarfs, let us continue to planets, to the worlds around other stars that Webb was designed to study. Exoplanet science has been transformed over the past 3 decades. From 0 confirmed planets around other stars to thousands cataloged, we have learned that planets are common, diverse, and often unlike anything in our solar system. Webb contributes by characterizing exoplanet atmospheres. When a planet passes in front of or behind its star, small amounts of the planet's atmospheric light can be isolated from the stellar glare. Spectroscopy of this light reveals which molecules are present, constraining the planet's composition and conditions. Webb has performed such observations for dozens of exoplanets. The results have been spectacular and puzzling in equal measure. Hot Jupiters, gas giants orbiting close to their stars, show atmospheric compositions that partially match predictions. Water vapor is detected as expected. Carbon dioxide appears in some cases. Sulfur dioxide, produced by photochemistry, has been found in several atmospheres. But the details often diverge from models. The abundances of detected molecules do not always match chemical equilibrium calculations. Species are present that should be destroyed at the observed temperatures, or absent when they should be abundant. The atmospheres are out of equilibrium, driven by processes that models do not fully capture. Vertical mixing is one explanation. If atmospheric circulation rapidly transports material between layers of different temperature, the chemical composition can be frozen in a state that reflects deeper, hotter regions rather than the upper atmosphere where observations probe. Photochemistry is another explanation. Ultraviolet light from the host star can break apart molecules and produce species that would not form through thermal chemistry. The effects depend on the stellar spectrum. the atmospheric composition, and dynamical processes that are poorly constrained. Neither explanation fully accounts for the observations. The disequilibrium is real, but its causes remain incompletely understood. For smaller planets, the situation is even more uncertain. Sub-Neptunes, planets between Earth and Neptune in size, are the most common type of exoplanet discovered by transit surveys. They have no solar system analog, and their internal structures and atmospheric compositions are largely unknown. Webb has attempted to characterize sub-Neptune atmospheres. In most cases, the observations are dominated by hazes or clouds at high altitudes that obscure the deeper atmosphere. Molecular features are muted or absent, hidden behind screens of tiny particles whose composition is unknown. Why are sub-Neptune atmospheres so hazy? The particles could be hydrocarbon hazes produced by photochemistry. They could be sulfur compounds. They could be silicates lofted from magma oceans below. Each possibility implies different underlying conditions, but Webb cannot distinguish between them. The haziness is frustrating because sub-Neptunes might hold clues to planetary formation and evolution. Their masses and radii suggest they could be water-rich worlds, mini-Neptunes with hydrogen envelopes, or something else entirely. Atmospheric characterization was supposed to discriminate between these possibilities. Instead, the atmospheres remain hidden. Webb sees the hazes, not what lies beneath. For rocky planets, the challenges are even greater. Small planets have thin atmospheres that produce weak spectroscopic signals. Even with Webb's sensitivity, detecting and characterizing rocky planet atmospheres is at the edge of feasibility. A few attempts have been made. For planets orbiting small, cool red dwarf stars, where the planet-to-star contrast is more favorable, Webb has searched for atmospheric signatures. The results are mostly non-detections. The planets examined so far show spectra consistent with bare rock. No substantial atmosphere detected. This could mean the planets genuinely lack atmospheres, stripped away by the intense radiation from their young host stars. Or it could mean the atmospheres exist, but in forms that Webb cannot detect, perhaps dominated by species without strong infrared features. These non-detections have implications for habitability. If rocky planets around red dwarfs typically lack atmospheres, they cannot support liquid water on their surfaces. The most common type of star in the universe might not host habitable worlds, narrowing the search for life. But the sample is small, and the conclusions tentative. Webb has observed only a handful of rocky planets in detail. The broader population remains uncharacterized. Let us step back from individual planets to the systems that contain them, to the protoplanetary disks where planets form. Protoplanetary disks are the birthplaces of solar systems, flattened structures of gas and dust orbiting young stars. They contain the raw material from which planets coalesce. Understanding disks is essential for understanding how planets come to be. Webb has observed protoplanetary disks with clarity that reveals structures invisible to previous telescopes. Gaps and rings in the dust distribution, spiral patterns in the gas, asymmetries and warps that suggest dynamical activity. These structures were initially interpreted as signposts of planet formation. A forming planet would carve a gap in the disk as it accretes material. The gap's width and depth would indicate the planet's mass. But Webb has found structures in disks too young to host the planets that would explain them. Some disks around stars barely 1 million years old already show multiple gaps and rings. Planet formation theory does not produce giant planets this quickly. Something else must be creating the structures. Alternative mechanisms have been proposed. Condensation fronts, where specific volatile species freeze out of the gas, could create opacity variations that appear as gaps. Magnetic fields interacting with ionized disk gas could produce zones of different density. Gravitational instabilities could generate spiral patterns without requiring planets. Each mechanism makes predictions about where structures should appear and what properties they should have. But distinguishing between mechanisms requires observations that probe disk physics at levels Webb cannot quite reach. The disk structures remain unexplained. They might mark forming planets. They might reflect disk physics we do not understand. The ambiguity persists. Webb has also measured the molecular composition of protoplanetary disks, detecting water vapor, carbon dioxide, and other species in the inner regions where terrestrial planets might form. The water abundance varies dramatically from disk to disk, more than models predict. Some inner disks are water-rich, some water-poor, for reasons that are unclear. The variation would affect the water content of any planets forming in those regions, with implications for habitability. What determines whether a disk is water-rich or water-poor? The initial composition of the cloud that collapsed to form the star? The disk's thermal history, which determines where water exists as vapor versus ice. Transport processes that move water-bearing solids inward or outward. All these factors contribute. Disentangling them requires understanding disk physics at levels we have not yet achieved. Webb has revealed the diversity. Explaining it remains for future work. From planet formation to the end of planetary systems, to stars that are dying, and what happens to any planets they host. When a sun-like star exhausts its hydrogen fuel, it swells into a red giant, expanding to hundreds of times its original radius. The inner planets are engulfed, vaporized, absorbed into the stellar envelope. What happens to outer planets, or to the debris left by destroyed planets, remains uncertain. Webb has observed planetary systems around dying and dead stars, searching for survivors and remnants. Around some white dwarfs, the dense remnants left after red giants shed their outer layers. Webb has detected infrared excess indicating the presence of warm dust. This dust likely comes from asteroids or planetary bodies that ventured too close to the white dwarf and were torn apart by tidal forces. The composition of this dust can be measured spectroscopically, revealing what the destroyed bodies were made of. The measurements provide unique windows into the compositions of extrasolar planetary material, information otherwise inaccessible. The compositions are surprising. Some white dwarf dust shows evidence of differentiated bodies, objects that had separated into core and mantle like Earth. This implies that substantial planetesimals survived the red giant phase and only later fell into the white dwarf. The survival itself is puzzling, requiring specific orbital configurations that models struggle to produce. Other white dwarf dust shows unusual elemental ratios, different from solar system asteroids, suggesting that planetary formation in other systems proceeded differently than in our own. Webb has revealed this material, the debris of alien worlds. What it means for planetary formation and evolution is still being worked out. The debris around white dwarfs connects to a broader question. What is the ultimate fate of planetary systems? Stars do not live forever. They exhaust their fuel, expand, contract, explode, or fade. The planets that orbit them must cope with these transformations or perish. For systems around Sun-like stars, the red giant phase is the critical challenge. The star expands, its luminosity increases, its mass loss intensifies. Inner planets are consumed. Outer planets may survive, but their orbits shift as the star sheds mass. Webb cannot observe planets around red giants directly. They would be lost in the stellar glare. But it can observe the aftermath, the white dwarf systems where survivors might remain. Searches for planets around white dwarfs have yielded few detections. The gravitational signatures are subtle. The transits are brief. The surveys are incomplete. But the non-detections are themselves informative. If planets commonly survived the red giant phase, we should see more of them. Their scarcity suggests that survival is difficult, that most planetary systems are disrupted or destroyed as their stars evolve. This has implications for the long-term habitability of the universe. If planetary systems have limited lifespans, the window for life to arise and persist is bounded not just by stellar main sequence lifetimes, but by the chaos of stellar death. Webb contributes one piece of this puzzle. Many pieces remain missing. Let us turn from dying systems to something more mysterious. Two objects that exist between galaxies, in the vast spaces where almost nothing should reside. Intergalactic space is not entirely empty. Diffuse gas permeates the cosmic web, filling the filaments that connect galaxy clusters. This gas is hot, ionized, and extremely sparse, detectable primarily through its absorption of light from background quasars. But there are also stars between galaxies. Not many, but some. Stars that have been stripped from their parent galaxies through tidal interactions, flung into the void to wander alone. These intergalactic stars are difficult to study. They are faint, scattered, and far from any galactic structure that might help identify them. Yet they carry information about the violent histories of the galaxies that produced them. Webb has observed the diffuse light from intergalactic stellar populations and galaxy clusters. This intracluster light, produced by stars belonging to no individual galaxy, reveals the accumulated debris of billions of years of tidal stripping. The amount of intracluster light varies widely between clusters. Some clusters glow with substantial halos of orphaned stars. Others show almost none. The variation does not correlate simply with cluster mass or dynamical state. What determines how much stellar material is liberated into intergalactic space? The merger histories of individual galaxies? The orbits on which galaxies fall into clusters? The concentration of dark matter halos, which affects how easily stars are stripped? All these factors likely contribute, but disentangling them requires understanding cluster formation in detail that current models do not provide. Webb has measured the intracluster light. Explaining its variation remains incomplete. There is another intergalactic puzzle: the missing baryons. Baryons are the particles that make up ordinary matter: protons, neutrons, and electrons. The total amount of baryonic matter in the universe is known from measurements of the cosmic microwave background and from the abundances of light elements produced in the Big Bang. But when astronomers count up the baryons in stars, gas, and other visible structures, the total falls short. Roughly half the baryons are missing, unaccounted for in any observed reservoir. Where are they? The leading hypothesis places them in the warm-hot intergalactic medium, gas at temperatures between 100,000 and 10 million Kelvin. too cool to emit detectable X-rays, but too hot to produce strong absorption in the optical or ultraviolet. This warm-hot gas should fill the cosmic web, tracing the filaments that connect galaxy clusters. Detecting it requires observations at specific wavelengths, where its faint emission or absorption might be visible. Webb's infrared observations do not directly probe the warm-hot intergalactic medium, but they contribute indirectly by mapping the structures where this gas should reside, by measuring the properties of galaxies embedded in filaments, by constraining the environments where the missing baryons might hide. The baryons remain missing. Webb has not found them, but it has helped define where to look. From missing matter to something equally elusive, the nature of dark energy. Dark energy comprises roughly 68% of the total energy content of the universe. It drives cosmic acceleration, causing the expansion of space to speed up rather than slow down. Its discovery in 1998 through observations of distant supernovae revolutionized cosmology. But what is dark energy? The simplest model treats it as a cosmological constant, a fixed energy density inherent to space itself. This model fits most observations, but it raises profound questions. If dark energy is a cosmological constant, its value is extraordinarily small compared to what quantum field theory predicts. The discrepancy spans over 100 orders of magnitude, the largest mismatch between prediction and observation in all of physics. Why is the cosmological constant so small? And why does it happen to have a value that allows structure and life to exist? A slightly larger value would have caused space to expand so rapidly that galaxies never formed. These questions have no answers within current physics. They point towards something fundamentally incomplete in our understanding. Webb contributes by constraining dark energy's properties across cosmic time, by measuring how galaxies cluster, how structure grows, how expansion has evolved. Webb tests whether dark energy is truly constant or whether it changes. Early results hint at possible evolution. Dark energy might have been slightly different in the past than it is today. The hints are not statistically definitive, but they persist across multiple analyses. If dark energy evolves, the cosmological constant interpretation is wrong. Something more complex is at work, perhaps a dynamical field that changes over time, perhaps modifications to general relativity on cosmological scales, perhaps physics we have not yet conceived. Webb alone cannot resolve this question, but it adds data that future analyses will incorporate, constraints that narrow the range of possibilities. The dark energy puzzle connects to another cosmological tension, the Hubble tension. The Hubble constant measures how fast the universe is expanding. It should be a single number, the same regardless of how it is measured. But different methods give different answers. Measurements based on the cosmic microwave background, extrapolated forward through cosmic history, using our standard cosmological model, give a Hubble constant of approximately 67 kilometers per second per megaparsec. Measurements based on nearby distance indicators, calibrated through chains of overlapping methods, give approximately 73. The difference is about 9%. This discrepancy exceeds the estimated uncertainties. If both measurements are correct, something about our cosmological model is wrong. Webb has contributed to the local measurement by observing Cepheid variable stars and other distance indicators with unprecedented precision. Its observations confirm the higher local value, ruling out some systematic errors that might have biased previous measurements. The tension persists. What could explain it? Perhaps dark energy evolves in ways that affect expansion differently at early and late times. Perhaps additional particle species existed in the early universe, altering the expansion history. Perhaps our model of cosmic evolution is wrong in ways we have not identified. Each possibility has implications. Each can be tested with future observations. But for now, the tension remains unresolved, a crack in the foundation of precision cosmology. Webb has sharpened the problem. It has not solved it. Let us shift from cosmology to something closer to home, to the objects within our own galaxy that Webb has illuminated. The Milky Way is not a pristine spiral. It bears the scars of billions of years of accretion and merger. Smaller galaxies have fallen into it, been torn apart by tidal forces, and left behind streams of stars that trace their former orbits. These stellar streams are fossils, recording the assembly history of our galaxy. By mapping them, astronomers reconstruct the sequence of events that built the Milky Way into its present form. Webb cannot survey the entire Milky Way. Its field of view is too narrow for that task. But it can observe individual streams and the remnants of disrupted systems with sensitivity that reveals details invisible to other telescopes. Some observations have been surprising. Certain stellar streams contain stars with unusual chemical compositions, signatures that do not match any surviving dwarf galaxy in the Milky Way's halo. The progenitors of these streams were chemically distinct systems that no longer exist as coherent objects. What were these progenitors? How did they evolve differently than surviving dwarfs? Why were they accreted while others survived? The answers require understanding the diversity of small galaxies in the early universe, before the Milky Way cannibalized many of them. Webb's observations of distant dwarf galaxies provide context, but connecting the distant population to the specific progenitors of Milky Way streams is difficult. The streams hold memories of galaxies we will never observe directly. Webb has helped read those memories imperfectly. There are other Milky Way mysteries that Webb has touched. The structure of the galactic center. The center of our galaxy harbors a supermassive black hole surrounded by dense clusters of stars, clouds of molecular gas, and structures shaped by intense radiation and gravitational forces. It is one of the most extreme environments in the local universe. Optical observations of the galactic center are impossible. Dust along the line of sight absorbs visible light completely. Only infrared and radio waves penetrate, revealing the crowded, chaotic region around the black hole. Webb has observed the galactic center with resolution and sensitivity that surpass previous infrared telescopes. Its images reveal structures previously unseen, filaments and arcs and features whose origins are debated. Some features suggest magnetic activity, fields strong enough to shape the distribution of gas and dust. Others suggest outflows from past episodes of black hole activity, bubbles and cavities carved by jets or winds. Still others remain unexplained, structures that do not match any model of what should exist in this environment. The galactic center is a laboratory for extreme physics, but it is a messy laboratory where multiple processes operate simultaneously, and distinguishing their effects is challenging. Webb has added clarity in some respects and complexity in others. The picture is not yet complete, from the galactic center to the farthest reaches of observation, to the frontier of observable reality. The cosmic microwave background marks the surface of last scattering, the moment roughly 380,000 years after the Big Bang when the universe became transparent to light. Before this moment, the universe was opaque, and no electromagnetic radiation from earlier times can reach us. This is a fundamental limit. Webb cannot see beyond the cosmic microwave background because there is nothing electromagnetic to see. The earliest photons we can detect were released at this epoch. But Webb can approach this limit. By observing galaxies at the highest redshifts, Webb probes the era just after the universe became transparent, the epoch when the first stars and galaxies were forming. At redshifts exceeding 10, corresponding to less than 500 million years after the Big Bang, Webb has found galaxies. Not many, but some. Objects that represent the earliest generation of cosmic structure. These earliest galaxies are faint, often detected at the edge of Webb's sensitivity. Their properties are uncertain, their masses and star formation rates estimated with large error bars. But their existence is confirmed. What do they tell us? They tell us that galaxy formation began early, that enough dark matter had clumped together within a few hundred million years to host stellar systems, that the universe transitioned from darkness to light relatively quickly. But the details remain murky. How did the first stars form? How massive were they? How did their light begin to ionize the intergalactic hydrogen? When exactly did reionization complete? Webb has constrained these questions. It has not answered them definitively. The epoch of reionization is one of the least understood periods in cosmic history. We know it happened, that the universe transitioned from neutral to ionized hydrogen. Sometime in the first billion years, we can measure when it ended by observing the absorption of light from high redshift quasars. But how it proceeded, which sources provided the ionizing photons, how patchy the process was, these remain uncertain. Webb has observed galaxies during the reionization epoch, measuring their ultraviolet luminosities and trying to estimate how much ionizing radiation they produced. The measurements suggest that the detected galaxies might be sufficient to reionize the universe, if their ionizing photon production and escape were efficient enough. But efficiency is hard to measure. Ionizing photons are absorbed by hydrogen, so we cannot observe them directly from high redshift sources. We must infer their production from other properties, and the inferences are model dependent. The reionization story remains incomplete. Webb has added chapters, but the narrative arc is still unclear. Let us consider something that Webb has observed extensively, but that remains poorly understood. Active galactic nuclei. At the centers of some galaxies, supermassive black holes are actively accreting matter. As material spirals inward, it heats to extreme temperatures and radiates across the electromagnetic spectrum. These active galactic nuclei can outshine their entire host galaxies, visible across billions of light years. Active nuclei come in varieties. Quasars are the most luminous, bright enough to be seen at the edge of the observable universe. Seyfert galaxies have active nuclei that are luminous but not dominant over the stellar light. Low ionization nuclear emission line regions, or liners, show weaker activity that may arise from different physical processes. Unified models attempted to explain this diversity as geometric effects. The same physical system, viewed from different angles, would appear as different types of active nuclei. Dust distributed in a torus around the central engine would block some lines of sight, but not others. Webb's infrared observations can penetrate dust that obscures optical views. They should reveal the hidden nuclei predicted by unified models, confirming that obscured and unobscured objects are fundamentally similar. Some observations support this picture, but others reveal genuine diversity that geometry alone cannot explain. Some active nuclei show spectral properties that require different accretion physics, not just different viewing angles. Others show variability on timescales too short for standard accretion disk models. Still others show evidence of multiple emission mechanisms operating simultaneously. The unified model is not wrong, but it is incomplete. Active nuclei are more diverse than geometry alone can produce. Webb has documented this diversity. Understanding what drives it remains a challenge. There is a particular category of active nuclei that Webb has studied with surprising results. The changing look, active galactic nuclei. These objects transition between active and quiescent states on timescales of months to years. A galaxy that appeared to host a luminous nucleus fades to show only stellar light. Or a previously quiet galaxy suddenly flares with nuclear activity. Standard models do not predict such rapid changes. The accretion disk around a supermassive black hole is vast, spanning light days to light weeks. Changes in the fuel supply should take much longer to propagate through the disk and affect the observed emission. What causes the rapid transitions? One possibility is that obscuring material moves across our line of sight, blocking and revealing the nucleus without any change in intrinsic activity. But the spectral changes in some objects are inconsistent with simple obscuration. Another possibility is that the inner accretion disk responds to instabilities that can develop and dissipate rapidly. Theoretical work suggests such instabilities might exist under specific conditions, but the physics is uncertain. A third possibility involves tidal disruption events, where stars or other objects pass close to the black hole and are torn apart. The debris produces a flare that fades as the material is consumed. Webb has observed changing look nuclei, tracking their spectral evolution and constraining the mechanisms. The observations support different explanations in different objects, suggesting that changing look behavior arises from multiple causes. The phenomenon remains incompletely understood. Webb has added data. Interpretation continues, from active nuclei to something quieter, to galaxies that have stopped forming stars. Quiescent galaxies, sometimes called red and dead galaxies, contain old stellar populations, but no ongoing star formation. They are common in the present-day universe, particularly among the most massive galaxies in cluster environments. How do galaxies become quiescent? Multiple mechanisms have been proposed. Active galactic nucleus feedback can heat or expel the gas needed for star formation. Environmental effects like ram pressure stripping can remove gas as galaxies move through cluster environments. Simple exhaustion of fuel can leave galaxies starving. The relative importance of these mechanisms depends on environment, mass, and cosmic epoch. Disentangling them requires observing galaxies in various stages of the quenching process. Webb has observed galaxies caught in transition, systems showing signs of declining star formation without yet reaching full quiescence. These transitional galaxies occupy the green valley between the blue star-forming cloud and the red quiescent sequence. The observations reveal diversity in quenching pathways. Some transitional galaxies show clear signs of active nucleus feedback, with spectral features indicating gas being heated or expelled by the central black hole. Others show environmental signatures, truncated gas disks, asymmetric star formation, evidence of ram pressure stripping. Still others show neither, transitioning for reasons observations cannot identify. The diversity suggests that quenching operates through multiple channels, with different mechanisms dominating in different circumstances. No single explanation accounts for all transitional galaxies. Webb has documented the diversity. A unified theory of quenching remains elusive. Let us turn to the chemistry of the universe, to the elements that make up everything we observe. The Big Bang produced hydrogen and helium, with trace amounts of lithium. Everything heavier was forged in stars, through nuclear fusion in stellar cores, and through explosive processes in supernovae and neutron star mergers. This chemical evolution is written in the spectra of stars and galaxies. By measuring element abundances across cosmic time, astronomers trace the history of nucleosynthesis, the accumulation of heavy elements over billions of years. Webb has contributed by observing element abundances at higher redshifts than previously accessible, probing the chemistry of the early universe directly. The observations reveal complexity beyond simple models. The ratio of alpha elements to iron varies in ways that trace different enrichment timescales. Alpha elements like oxygen and magnesium are produced primarily in core collapse supernovae, the deaths of massive stars that live only millions of years. Iron is produced in significant quantities by type Ia supernovae, thermonuclear explosions of white dwarfs that occur on longer timescales. In the early universe, where there has not been time for many type Ia supernovae, the alpha to iron ratio should be elevated. Webb has confirmed this in some early galaxies, but the ratios vary more than models predict. Some early galaxies show extremely elevated alpha to iron, suggesting almost pure core collapse enrichment. Others show surprisingly solar-like ratios, suggesting type Ia contributions earlier than expected. What determines these variations? The initial mass function, which affects how many massive stars form and explode as core collapse supernovae. The star formation history, which determines when different enrichment channels contribute. Galactic winds, which might preferentially expel material enriched by one channel or another. All these factors influence the outcome. Predicting the chemistry of any given galaxy requires understanding all of them in detail that models do not yet achieve. Webb has measured the variations. Explaining them requires theoretical advances still in progress. There is another chemical puzzle that Webb has illuminated: the origin of nitrogen. Nitrogen is produced through the CNO cycle in stellar cores, where carbon and oxygen serve as catalysts for hydrogen fusion. The process requires carbon and oxygen to already be present, meaning nitrogen enrichment should lag behind other elements. But some early galaxies show nitrogen abundances that are surprisingly high given their overall metallicity. The nitrogen to oxygen ratio exceeds what standard stellar evolution produces. What is producing the excess nitrogen? One possibility involves very massive stars, objects above 100 solar masses that might have been common in the early universe. These stars process material through the CNO cycle rapidly, potentially producing nitrogen more efficiently than lower mass stars. Another possibility involves rapidly rotating massive stars, where rotation-induced mixing brings nitrogen-rich material from the core to the surface, where stellar winds can disperse it. A third possibility involves Wolf-Rayet stars, evolved massive stars with strong winds that expose their nitrogen-enriched cores. Each mechanism has different requirements and predictions. Distinguishing between them requires understanding the stellar populations of early galaxies in detail that observations cannot yet provide. Webb has detected the nitrogen excess. The source remains debated. Let us consider something that connects multiple puzzles we have discussed: the intergalactic medium. Between galaxies, filling the cosmic web, lies a sparse ocean of gas. This intergalactic medium is mostly ionized hydrogen, with traces of heavier elements dispersed by galactic winds and other processes. The intergalactic medium affects observations in subtle but important ways. Light from distant quasars passes through this gas, acquiring absorption features that reveal the medium's properties. By analyzing these absorption spectra, astronomers map the distribution and state of intergalactic gas across cosmic time. Webb has extended these observations to higher redshifts, probing the intergalactic medium during and before the epoch of reionization. The observations reveal patchiness. Some lines of sight show strong absorption from neutral hydrogen, indicating regions where reionization had not yet completed. Others show weak absorption, indicating ionized regions. The variation is larger than models typically produce. What created this patchiness? The distribution of ionizing sources, with some regions bathed in ultraviolet light while others remained in shadow. Variations in gas density, with overdense regions remaining neutral longer than underdense ones. Recombination in dense pockets, where ionized hydrogen could neutralize faster than sources could ionize it. All these factors contribute. Modeling the patchy reionization requires understanding the early source population and the gas distribution simultaneously, a challenge that current simulations only partially meet. Webb has revealed the patchiness. Explaining it fully requires advances in both observation and theory. The intergalactic medium also contains metals, heavy elements transported from galaxies by winds and outflows. These metals produce absorption features at specific wavelengths, allowing astronomers to trace enrichment across cosmic time. Webb has detected metals in the intergalactic medium at high redshifts, confirming that enrichment began early. But the distribution is uneven. Some regions show strong metal absorption. Others, at similar redshifts, show weak or absent absorption. The variation is larger than models predict, suggesting that metal transport is more complex than simple wind models assume. How did metals reach some regions and not others? How far did early galactic winds travel? How efficiently did they mix with the surrounding medium? These questions bear on understanding cosmic chemical evolution and the conditions under which planets and life might arise. Webb has added data points. The full picture remains unclear. We have journeyed through a landscape of mysteries, from the foundations of cosmology to the chemistry of the intergalactic medium, from the first galaxies to the planets around nearby stars. At every turn, Webb has revealed complexity beyond expectation. What does this pattern mean? One interpretation is that our models are too simple. Built on assumptions appropriate for the data available before Webb, they naturally fail when confronted with Webb's superior observations. This is normal scientific progress, and the models will improve. Another interpretation is that something deeper is wrong. Multiple tensions across different domains might point toward fundamental physics we are missing. Dark matter that behaves differently than assumed. Dark energy that evolves. Initial conditions more complex than inflation predicts. A third interpretation is that the universe is simply messier than we hoped. Real objects are diverse, shaped by histories and environments that vary widely. The clean predictions of idealized models will always fail in detail, even if they capture broad trends. Perhaps all three interpretations contain truth. Models are too simple, physics may be missing, and the universe is indeed messy. Science proceeds by grappling with all these possibilities, testing each against new observations. Webb has provided those observations. The grappling continues. Let us pause to appreciate what Webb has accomplished, even as we catalog its silences. The telescope has operated beyond specifications. Its mirror is more precisely aligned than engineers hoped. Its instruments are more sensitive than requirements demanded. Its orbit is stable. Its fuel reserves sufficient for decades of operation. The images it has returned have transformed public perception of the cosmos. The deep fields, crowded with galaxies. The nebulae, intricate with structure. The planets, resolved with unprecedented clarity. These images have inspired millions who will never read a scientific paper. But inspiration is only part of the mission. Webb was built for science, for pushing the boundaries of knowledge, for testing our understanding against the universe itself. In this mission, Webb has succeeded by failing. It has found our understanding wanting. It has revealed where our models break down. It has posed questions we did not know to ask. This is exactly what a great observatory should do. The silences Webb has left are not failures. They are invitations. They call future scientists to think harder, observe more carefully, build better models. They mark the frontier of knowledge and challenge us to push that frontier outward. The frontier will be pushed. It always is. Each generation of astronomers stands on the shoulders of those who came before, seeing further because others built the foundations. Webb is the latest foundation. Others will build upon it. What will they find? We cannot know. The history of science is a history of surprises. The discoveries that matter most are usually the ones no one anticipated. Dark energy was not predicted before it was discovered. Exoplanets were theorized, but their diversity was not imagined. The cosmic microwave background was found by accident. Future discoveries will surprise us equally. They will emerge from data already in hand, waiting to be noticed. They will come from observations not yet made, probing regions and objects we have not yet examined. They will arise from theoretical insights that connect disparate phenomena in ways currently unseen. Webb has set the stage for these discoveries. It has gathered the data, posed the questions, revealed the anomalies. The discoveries will follow, and when they come, they will not end the quest. They will open new questions, new mysteries, new silences to fill. This is the nature of science. The universe is larger than our minds, and our understanding will always be incomplete. But incomplete is not the same as absent. We know vastly more than we did a century ago, a decade ago, a year ago. The knowledge accumulates imperfectly but persistently. Each observation adds to the edifice. Each theory refines the picture. Each generation passes to the next, a richer understanding than it inherited. Webb is part of this chain. Its observations will be studied for decades, its data mined for discoveries long after the telescope itself has ceased operating. The questions it has posed will drive research for a generation. The answers, when they come, will raise new questions for the generation after. This is the work of science. Endless, humbling, exhilarating. The telescope floats at its gravitational balance point, 1,000,000 miles from Earth. Its golden mirror catches ancient light. Its instruments sort photons by energy and direction. Its transmitters beam data back to a small blue world where curious creatures try to make sense of it all. Those creatures are us. We built this telescope. We launched it into the void. We analyzed its data and wrote papers and argued about interpretations. We are the ones who must grapple with the mysteries it reveals. The grappling is what makes us human. The drive to understand, to explain, to find patterns in chaos, the willingness to admit ignorance and seek to remedy it. The persistence to keep asking questions even when answers are slow to come. Webb has given us much to grapple with. The gift is precious. The work continues. What did James Webb not tell us about the universe? It did not tell us why the universe is so smooth on large scales, yet structured so quickly on small scales. It did not tell us what dark matter is made of, or why it clumps the way it does. It did not tell us whether dark energy is constant or evolving. It did not tell us how the first galaxies formed so quickly, or why they look so mature. It did not tell us what creates the hazes in exoplanet atmospheres, or why subneptunes are so common. It did not tell us how supermassive black holes grew so large so fast. It did not tell us why the Hubble tension exists, or how to resolve it. It did not tell us where half the baryons are hiding. It did not tell us what causes the chemical anomalies in early galaxies. It did not tell us how reionization proceeded in such patchy fashion. These silences are not answers. They are questions, sharper now than before Webb launched. They define the frontier of our ignorance, the territory where discovery awaits. The universe keeps its secrets, but it reveals them, gradually, to those patient and clever enough to look. Webb has looked. It has seen wonders beyond imagination and puzzles beyond current understanding. Both are gifts. The wonders remind us why we explore, the beauty of distant galaxies, the intricacy of nebulae, the diversity of worlds. These are reasons to look up, to be curious, to spend resources and effort understanding our cosmic context. The puzzles remind us how much remains to learn. They prevent complacency, the assumption that we have figured everything out. They drive the next generation of observations, theories, and discoveries. Webb has provided both wonders and puzzles in abundance. The story is not over. It is never over. The universe has been here for 13.8 billion years and will continue for trillions more. Our species has been looking up for only a few millennia, understanding what we see for only a few centuries, building space telescopes for only a few decades. We are at the beginning, not the end. The questions Webb has raised will be answered, and those answers will raise new questions. The process will continue as long as curious minds exist to pursue it. And somewhere out there, beyond the farthest galaxies Webb can see, beyond the cosmic horizon where light has not had time to reach us, the universe continues. Galaxies form, stars burn, planets orbit, and perhaps other curious minds look out at their sky and wonder. They will never know of us. We will never know of them. The distances are too vast, the universe too large. But we share the wondering. Wherever minds exist, they ask the same questions. What is out there? How did it come to be? What does it mean? The questions are universal, even if the answers vary. They connect us to every intelligence that has ever looked up at the night sky, on any world, in any galaxy, at any time. Webb has deepened those questions. It has not diminished them. That is its greatest gift. The telescope orbits, silent and cold, collecting photons from across the cosmos. It does not know what it sees. It does not understand the significance of its data. It is an instrument, exquisitely crafted, beautifully engineered, doing exactly what it was designed to do. We are the ones who must find meaning in the data. We are the ones who must connect observation to understanding, measurement to insight. We are the ones who ask why and struggle toward answers. The answers will come. Slowly, incompletely, always raising new questions. But they will come. And when they do, we will look back at Webb as a turning point. The telescope that showed us how much we did not know. The observatory that revealed the universe's true complexity. The eye that opened our own eyes to mysteries we had not imagined. The silences it left behind are not empty. They are full of possibility. They are the sound of the next discovery, waiting to be made. Понял? Давайте пересчитаем. Ваши данные. 95 тысяч символов. Урья 90 минут. Скорость 95 тысяч. 90. Ури. Нанарен. И 56 символов в минуту. Для дополнительных 50 минут 50x айнаден 0,56 на 53 тысячи символов. Начинаю писать продолжение. 53 тысячи символов, которое логически продолжит вторую часть. The answers will come. But while we wait for them, let us explore further into the territories Webb has mapped. There are regions of cosmic structure that deserve closer attention. The filaments themselves, the threads of the cosmic web that connect galaxy clusters across hundreds of millions of light years. These filaments are not uniform. They vary in thickness, in density, in the galaxies they contain. Some are highways of cosmic traffic, channeling matter from the diffuse intergalactic medium toward the massive clusters at their endpoints. Others are quieter, thinner, carrying less material through less dramatic gravitational gradients. Webb has observed galaxies within filaments, comparing their properties to galaxies in clusters and in the field. The observations reveal that environment shapes evolution even before galaxies reach the dense cluster cores. Filament galaxies show intermediate properties. Their star formation rates are lower than field galaxies, but higher than cluster members. Their gas content is reduced, but not eliminated. Their morphologies are transitioning, spirals beginning to fade, disks beginning to thicken. This pre-processing, as astronomers call it, suggests that galaxy transformation begins long before a galaxy falls into a cluster. The filament environment itself, though less extreme than the cluster core, already affects how galaxies evolve. What causes this pre-processing? The gas in filaments, though sparse, is warmer than the general intergalactic medium. Galaxies moving through this gas might experience mild ram pressure, not enough to strip their gas entirely, but enough to disturb it, to trigger some star formation while suppressing other star formation, to begin the transition toward quiescence. Gravitational interactions also play a role. Filaments are not empty corridors. They contain other galaxies, and close passages between them can disturb disks, trigger starbursts, and initiate morphological changes. Webb has documented the pre-processing. The physics behind it is still being untangled. There is another aspect of filaments that Webb has probed: the gas that flows along them. Simulations predict that cold gas streams along cosmic web filaments, falling toward the nodes where clusters form. This cold flow accretion could be a major channel for galaxy growth, delivering fuel for star formation without the heating that occurs when gas falls through a hot cluster atmosphere. Detecting these cold flows observationally is difficult. The gas is sparse, its emission faint. But Webb can observe the effects of cold flows on the galaxies that receive them. Some galaxies show kinematic signatures consistent with cold accretion. Gas moving in coherent streams, aligned with the larger-scale filament structure, feeding star formation at rates that seem to require continuous fuel supply. But other galaxies in similar environments show no such signatures. Their gas is chaotic, their star formation sporadic, their accretion apparently disrupted or absent. What determines whether a galaxy receives cold flows smoothly or not? The mass of its dark matter halo? Its position within the filament? The thermal history of the surrounding gas? The answers remain unclear. Webb has observed the diversity. Explaining it requires theoretical models that capture the complexity of gas accretion in realistic cosmic environments, from filaments to the voids between them, the emptiest regions of the universe. Cosmic voids are not perfectly empty. They contain some galaxies, some gas, some dark matter, but their density is far below the cosmic average, making them laboratories for studying galaxy evolution in isolation. Void galaxies evolve differently than their counterparts in denser environments. Without frequent interactions, they experience less disturbance. Without hot surrounding medium, they retain their gas longer. Without nearby clusters, they never experience the extreme environmental effects that transform cluster members. Webb has observed void galaxies at higher redshifts than previously possible, tracing how isolation affects evolution across cosmic time. The void galaxies are bluer, indicating ongoing star formation. They are more disk-dominated, their spirals undisturbed by interactions. They are more gas-rich, retaining fuel that denser environments would have stripped away. But within these trends, there is scatter. Some void galaxies are surprisingly red and quiescent, despite their isolated environments. Some show disturbed morphologies, despite having no obvious interaction partners. What is happening to these anomalous void galaxies? Have they experienced interactions we cannot detect, with companions now too faint or too distant to identify? Have internal processes, feedback from supernovae or active nuclei, affected their evolution without environmental triggers? Webb has documented the anomalies. Their origins remain uncertain. The voids themselves are growing. As the universe expands, matter drains from underdense regions toward the surrounding filaments and clusters. The voids become emptier, their boundaries sharper. This evolution affects the galaxies within them. A galaxy that once resided in a mildly underdense region now finds itself in a deeper void, more isolated than before. Its environment has changed not because it moved, but because the cosmic web evolved around it. Webb cannot track individual galaxies across cosmic time, but by observing void populations at different redshifts, it traces the statistical evolution of isolated systems. The observations suggest that void evolution is gentler than cluster evolution, but not negligible. Void galaxies do change over time, even without external disturbances. Internal processes, the slow consumption of gas, the gradual aging of stellar populations, shape their evolution over billions of years. This internal evolution is difficult to model. It depends on the details of star formation, on feedback processes, on the cycling of gas between interstellar and circumgalactic reservoirs. Current models capture the broad trends, but miss the details. Webb has added data points. The models are still catching up. Let us shift from large-scale structure to something more intimate. The binary systems that Webb has studied. Not binary stars, though Webb observes those too. Binary galaxies. Pairs of galaxies bound together by gravity, orbiting their common center of mass, destined eventually to merge. Galaxy pairs are laboratories for studying interaction physics. As two galaxies approach, tidal forces stretch and distort their structures. Gas is compressed at certain locations, triggering starbursts. Dark matter halos overlap and interpenetrate. The systems exchange angular momentum, their orbits decaying until they finally coalesce. This merger process has been studied extensively through simulations. The physics is complex but understood in principle. The simulations reproduce many features of observed merging systems. But Webb has found pairs that challenge the simulations. Some pairs show tidal features that extend farther than simulations predict. The debris stretches across hundreds of thousands of light years, farther than gravitational interactions should be able to fling material. Were these systems disturbed by additional companions, now no longer visible? Did the interaction occur under unusual conditions, with relative velocities or impact parameters that simulations rarely explore? Other pairs show enhanced star formation in regions where simulations predict quiescence. The starbursts occur in the tidal tails, far from the galactic centers, where gas density should be too low to support efficient star formation. What triggers this extended star formation? Compression by interactions with intergalactic gas? Cooling instabilities in the stretched tidal material? Physics that simulations do not capture? Webb has observed the unexpected starbursts. Their mechanism remains debated. The timing of mergers also presents puzzles. Simulations predict how long the merger process should take, from first approach through final coalescence. The timescale depends on the masses of the galaxies, their relative velocities, and the impact parameter of the encounter. When astronomers count merging systems at different stages and different redshifts, they can estimate how merger rates have evolved over cosmic time. These estimates should match the predictions of cosmological simulations. The match is imperfect. At some redshifts, observations suggest more mergers than simulations produce. At others, fewer. The discrepancies are not large, but they persist across different surveys and different analysis methods. What causes the mismatch? Selection effects that make some merger stages easier to identify than others. Limitations in the simulations which cannot resolve all the physics relevant to merger identification. Real differences between the universe and our models of it. Webb has added observations at redshifts where previous surveys were incomplete. The discrepancies have not vanished. They have become more precisely measured. More precise discrepancies are progress. They tell us where to focus theoretical effort, but they are not resolution. The merger rate puzzle remains open, from merging galaxies to their aftermaths, to the remnants left behind when two systems coalesce. Merger remnants should show specific properties. Their stellar populations should be mixed, containing stars from both progenitors. Their kinematics should be disturbed, with stars on box orbits and radial orbits rather than circular ones. Their central supermassive black holes should have grown through accretion of gas funneled by the merger, and eventually the two black holes should merge themselves. Webb has observed merger remnants at higher redshifts than previous telescopes could reach. These observations probe how quickly remnants settle after the violence of coalescence. Some remnants appear settled, their stellar distribution smooth, their kinematics relaxed. They have transformed into elliptical galaxies with little trace of their violent past. But the timescales are puzzling. Some systems appear settled within a few 100 million years of the merger, faster than dynamical relaxation should allow. The stars should still be on disturbed orbits. The phase space distribution should still show the scars of collision. How do merger remnants relax so quickly? Violent relaxation during the merger itself can redistribute energy among stars, speeding the approach to equilibrium. But whether violent relaxation is efficient enough to explain the observations is uncertain. Perhaps other processes contribute. Continued gas accretion after the merger might build a new disk component that dilutes the disturbed stellar population. Minor mergers with smaller companions might heat and reshape the remnant. Central black holes might affect the stellar distribution through dynamical feedback. Webb has observed the apparently settled remnants. The physics of their rapid relaxation is not fully understood. The black holes at the centers of merger remnants deserve special attention. When two galaxies merge, their central supermassive black holes sink toward the center of the combined system through dynamical friction. Eventually, they approach close enough that gravitational wave emission becomes efficient, and they spiral together and merge in one of the most violent events in the universe. The timescale for black hole merger depends on the stellar and gas environment. In some configurations, the black holes stall at separations of parsecs to kiloparsecs, unable to lose enough energy to continue their spiral. This is called the final parsec problem. Do black hole binaries actually stall, or do they find ways to continue merging? Webb cannot directly observe black hole binaries at parsec separations. The angular scales are too small, but it can observe the effects that binary black holes might have on their surroundings. Active galactic nuclei powered by binary black holes might show specific variability patterns, as the orbital motion modulates the accretion. Their jets might precess, wobbling as the black hole spins interact. Their host galaxies might show kinematic signatures of the gravitational influence of two massive central objects. Webb has searched for these signatures in galaxies thought to host binary black holes. Some show suggestive features, others do not. The evidence for binary black holes remains circumstantial. Direct confirmation awaits gravitational wave observations, or very long baseline imaging that can resolve the smallest separations. Webb has contributed pieces to this puzzle. The complete picture awaits future observations. Let us consider something that connects galaxies across cosmic time: the stellar mass function. The stellar mass function describes how many galaxies exist at each stellar mass. It is one of the most fundamental statistical descriptions of the galaxy population, encoding information about how galaxies form and evolve. The stellar mass function evolves with redshift. At early times, massive galaxies were rarer than they are today. The function has built up over cosmic time, as galaxies formed stars and grew through mergers. Webb has measured the stellar mass function at higher redshifts than previously possible. These measurements extend our knowledge of galaxy populations into the first billion years of cosmic history. The high redshift mass function shows surprises. There are more massive galaxies at early times than standard models predict. The excess is not enormous, but it is statistically significant. Something about galaxy formation allowed massive systems to assemble earlier than simulations typically produce. This connects to the rapid structure formation we discussed earlier. The universe seems to have been more efficient at building massive systems early than our models assume. What explains the excess? More efficient star formation in early galaxies, higher merger rates that built up mass faster, initial conditions that favored massive halo formation. Each possibility has implications for galaxy evolution models. Each can be tested with additional observations and refined simulations. But for now, the excess massive galaxies remain unexplained. The low mass end of the stellar mass function presents different puzzles. Small galaxies are difficult to detect at high redshifts. Their light is faint, spread across the sky, easily lost in the noise. Webb has pushed detection limits deeper than before, but incompleteness remains a concern. Accounting for incompleteness requires modeling which galaxies might be missed and how their omission affects the measured mass function. These corrections are uncertain, depending on assumptions about the properties of undetected galaxies. Different assumptions produce different corrected mass functions. The true abundance of small galaxies at high redshift remains uncertain by factors of several. This matters because small galaxies are the building blocks of hierarchical structure formation. If they were more or less abundant than models predict, the implications cascade through our understanding of galaxy assembly. Webb has improved the measurements. The uncertainties remain substantial. From the statistics of galaxy populations to the properties of individual systems, to the galaxies that deviate from the norm. Every galaxy sample contains outliers, systems whose properties place them far from the typical population, whose existence challenges our understanding of what is possible. Webb has found outliers at high redshifts that push against theoretical limits. Some galaxies appear to have converted essentially all their available gas into stars, achieving star formation efficiencies approaching 100%. Standard models predict efficiencies of a few percent at most, with the rest of the gas expelled by feedback or retained in non-star forming reservoirs. How did these maximally efficient galaxies form? Did feedback somehow fail to operate? Did gas cooling proceed so rapidly that stars formed before feedback could act? Are the mass estimates wrong, making the apparent efficiency an artifact of measurement error? Each possibility is being explored. None has been definitively confirmed. Other outliers show the opposite extreme. Galaxies with abundant gas but minimal star formation. Systems that should be vigorously producing stars but are not. What suppresses star formation in these gas-rich systems? Heating from active nuclei? Stabilization by angular momentum? Magnetic fields that support the gas against collapse? The suppression mechanisms are debated. Webb has observed the quiescent gas-rich galaxies. Their properties constrain but do not uniquely identify the responsible physics. Outliers are scientifically valuable precisely because they are extreme. They stress test our models, revealing where assumptions break down. The outliers Webb has found will drive theoretical development for years. Let us turn from outliers to a phenomenon that should be rare but keeps appearing. Gravitational lensing, producing unexpected configurations. Gravitational lensing occurs when mass bends light. when a massive foreground object lies along the line of sight to a more distant source. The source's image is distorted, magnified, sometimes multiplied into arcs and rings. The mathematics of gravitational lensing is well understood. Given a mass distribution, the resulting image configurations can be calculated precisely. Conversely, given observed image configurations, the mass distribution can be inferred. Webb has observed lensed systems with image configurations that are difficult to explain. Some systems show images at positions that do not match smooth mass models. The foreground lensing mass must be more complex, containing substructures that perturb the images. These substructures could be clumps of dark matter, small halos orbiting within larger ones. Their abundance and properties are predicted by cold, dark matter simulations. The lensing observations test these predictions. Some observations suggest more substructure than simulations produce. Others suggest less. The results depend sensitively on how the data is analyzed, on assumptions about the smooth component of the lens, on treatment of observational uncertainties. The substructure question remains contested. Different groups analyzing similar data reach different conclusions. The systematics of the analysis are not fully under control. Webb has added high-quality data. The analysis methods are still being refined. There is another lensing puzzle that Webb has illuminated: the magnification anomalies. When a lensed quasar appears as multiple images, the brightness ratios of those images should follow predictions based on the lens model. If the lens is smooth, the ratios are determined by simple geometry. Observed ratios often deviate from predictions. The anomalies are attributed to microlensing, where individual stars in the lensing galaxy briefly magnify or demagnify the quasar images as they pass in front. Microlensing is expected. It provides a tool for studying stellar populations in distant lensing galaxies. But the amplitude and frequency of microlensing variations sometimes exceed predictions. Are there more stars in the lensing galaxies than expected? Are the stars distributed differently than assumed? Is there additional compact mass, perhaps from primordial black holes, contributing to the microlensing? Primordial black holes are hypothetical objects formed in the early universe before stars existed. If they exist in significant numbers, they could contribute to dark matter and produce microlensing signatures distinguishable from stellar microlensing. Webb cannot directly detect primordial black holes, but by constraining the microlensing properties of lensing galaxies, it constrains the possible contribution of compact objects to the mass budget. The constraints are tightening. Primordial black holes are not ruled out, but their allowed abundance is shrinking. If they exist, they must be rare. Webb has contributed to this hunt. The quarry has not been caught. From lensing to something it enables. Observations of objects that would otherwise be too faint to study. Gravitational magnification by galaxy clusters and massive galaxies allows Webb to observe sources that would be undetectable without the boost. These lensed high redshift galaxies provide our best views of star formation and stellar populations in the early universe. But lensing introduces complications. The magnification varies across the source. Different parts of a galaxy are magnified by different amounts. Reconstructing the intrinsic properties requires modeling the lens and correcting for the magnification gradient. This modeling introduces uncertainties. Different lens models produce different reconstructions. The intrinsic size, luminosity, and morphology of the source depend on which model is adopted. Webb has observed lensed galaxies with multiple independent teams modeling the same systems. The reconstructions do not always agree. The disagreements are usually modest, within stated uncertainties. But they remind us that our knowledge of these most distant galaxies is filtered through lensing, and the filter is imperfect. For the most extremely magnified sources, the uncertainties are largest. The magnification can reach factors of tens or even hundreds, stretching the source into thin arcs where fine structure becomes visible. But interpreting that fine structure requires precise knowledge of the magnification map. Webb has resolved structures within highly magnified sources that no previous telescope could see. Star-forming clumps, apparently. Individual star clusters, perhaps. But the interpretation depends on lens modeling that carries inherent uncertainties. The lensed views are precious, but imperfect. Webb has exploited them extensively. The imperfections remain. Let us consider the cosmic infrared background, the accumulated glow of all infrared sources across cosmic history. Every star, every galaxy, every warm dust grain that ever emitted infrared light contributes to this background. It is the integral of cosmic infrared emission from the Big Bang to now. Measuring the cosmic infrared background is challenging. Foreground emission from the solar system and the Milky Way must be subtracted. Instrumental backgrounds must be characterized and removed. The extragalactic signal is small compared to these contaminants. Early measurements suggested more background light than could be accounted for by known galaxy populations. This excess sparked speculation about unknown sources, decaying dark matter, primordial black holes, ancient stellar populations that had faded below detectability. Webb has addressed this question by pushing galaxy counts to fainter limits. The more complete the count of individual sources, the less room remains for mysterious diffuse components. Current Webb counts can account for most of the measured background. The excess, if it exists, is smaller than earlier estimates suggested, but uncertainties remain. The faintest sources are at the edge of detectability, where completeness corrections are large and uncertain. The background measurements themselves have systematic uncertainties that are difficult to characterize. Whether a truly unexplained background excess exists is no longer clear. Webb has reduced the room for exotic explanations but has not eliminated it entirely. The cosmic infrared background connects to another measurement, the optical background, the accumulated glow of all optical sources. The optical background is even more difficult to measure than the infrared. Foregrounds are brighter. Instrumental effects are more severe. The extragalactic signal is fainter relative to contaminants. Webb operates primarily in the infrared, but its shortest wavelength observations touch the red end of the optical. These observations constrain the optical background from the extragalactic side. The constraints are consistent with galaxy counts, but do not dramatically improve our knowledge of the optical background. Other facilities, designed specifically for this measurement, will contribute more. Webb's contribution is incremental. Every increment helps, from backgrounds to foregrounds, to the dust in our own galaxy that complicates every extragalactic observation. Interstellar dust in the Milky Way absorbs and scatters light from distant sources. The effect depends on wavelength, with shorter wavelengths affected more strongly. This differential extinction reddens the observed colors of extragalactic objects. Correcting for galactic extinction requires knowing how much dust lies along each line of sight. Dust maps, constructed from stellar reddening measurements and far infrared emission, provide this information. But the maps are imperfect. They have limited angular resolution. They may miss small-scale variations in dust properties. They assume all dust has the same extinction law, which may not be true everywhere. Webb observes in the infrared, where extinction is less severe than at optical wavelengths, but it is not zero. For precision measurements, galactic extinction must still be corrected. For some Webb observations, particularly those through patchy regions of the Milky Way, the extinction corrections are uncertain. The error bars on corrected fluxes include contributions from imperfect dust modeling. This is not a failure of Webb. It is a reality of observing the universe from within a dusty galaxy. The foreground affects all extragalactic observations, and characterizing it perfectly is beyond current capability. Webb has revealed where the foreground corrections are most uncertain. Improving the dust maps requires dedicated observations that Webb was not designed to provide. The foreground dust connects to the dust in other galaxies, to the interstellar medium of external systems that Webb has studied in unprecedented detail. We discussed earlier that Webb has found dust with unexpected spectral properties, features that do not match standard grain compositions, emission that exceeds what absorbed light should produce. These anomalies appear across diverse environments, in star-forming regions of nearby galaxies, in the circumstellar environments of evolved stars, in the diffuse interstellar medium between star-forming complexes. The ubiquity of the anomalies suggests they are not peculiarities of specific objects. They reflect something general about interstellar dust that our models miss. What could that something be? The grain size distribution might differ from local Milky Way conditions. Smaller or larger grains would produce different spectral features. The environmental processes that grind, shatter, or coagulate grains might operate differently in different galaxies. The grain composition might be more varied than assumed. Standard models consider silicates and carbonaceous grains. But interstellar space contains many elements, and the chemistry of dust formation in stellar outflows is complex. Exotic grain species might be more common than recognized. The grain structure might matter. Porous grains, fluffy aggregates, core mantle structures, all would have different optical properties than solid homogeneous spheres. The assumed grain geometry might be too simplified. Webb has observed the anomalies. Laboratory work and theoretical modeling are needed to interpret them. The interpretation is ongoing, from dust to gas, to the molecular component of the interstellar medium. Molecules form in the densest, coldest regions of interstellar space, shielded from ultraviolet radiation that would dissociate them. They grow in complexity through surface reactions on dust grains and gas phase chemistry. The molecular inventory of interstellar clouds includes over 200 identified species. Simple molecules like water and carbon monoxide. Complex organic molecules with chains of carbon atoms. Even some molecules with prebiotic relevance, amino acid precursors and sugars. Webb has observed molecular emission and absorption in nearby star-forming regions and in external galaxies. Its spectroscopic capabilities identify molecules through their characteristic spectral fingerprints. Some observations confirm expectations. Water ice is abundant in cold cloud cores. Carbon monoxide traces molecular gas densities. The chemistry proceeds as models predict. But there are surprises. Some molecules appear in environments where they should be destroyed. Certain carbon chain species are detected in regions exposed to ultraviolet radiation that should rapidly dissociate them. Either they are being replenished very quickly, or they are shielded by structures smaller than observations can resolve. Other molecules are absent where they should be abundant. The nitrogen chemistry in some clouds does not match predictions based on measured nitrogen abundances. Either the nitrogen is sequestered in forms that spectroscopy does not detect, or the reaction networks contain errors. The molecular puzzles are specialists' concerns, but they connect to broader questions. The molecules that form in interstellar clouds are the raw material for planetary systems. The chemical inventory of a protoplanetary disk reflects the chemistry of the cloud from which it formed. Understanding interstellar chemistry is prerequisite to understanding the compositions of planets. Webb has added molecular detections. The chemical models are being updated. The connection to planet formation is being explored. Let us zoom out from the details to consider what Webb's observations collectively tell us about the state of astronomical knowledge. Every major observational advance in history has revealed the unexpected. Galileo's telescope showed mountains on the moon and moons around Jupiter, challenging the Aristotelian cosmos. Hubble's observations demonstrated that the universe is expanding, overturning the static universe that Einstein had assumed. The discovery of cosmic microwave background radiation confirmed the Big Bang and eliminated steady-state alternatives. Webb is in this tradition, not because it has overturned any fundamental theory, but because it has revealed the inadequacy of our detailed models. The broad outlines of cosmic evolution remain intact. The universe began with a Big Bang. Galaxies formed from gravitational collapse of primordial fluctuations. Stars synthesized heavy elements that accumulated in successive generations. But the details do not match. The timing is wrong. The efficiencies are unexpected. The diversity is greater than predicted. The smooth predictions of idealized models give way to messy reality. This is not crisis. It is opportunity. The discrepancies point toward physics we do not understand. They guide the development of better models. They ensure that astronomy will remain vibrant and productive for generations. Webb has created a research agenda that will outlast its operational lifetime. The data it has collected will be mined for decades. The questions it has raised will drive theory development for longer. This is the mark of a great observatory. Not that it answers all questions, but that it opens new ones. Not that it confirms expectations, but that it reveals surprises. Not that it completes our understanding, but that it extends the frontier. Webb has extended the frontier farther than any telescope before it. The objects it has observed span the full range of cosmic structure. Planets and their atmospheres, stars in all stages of life and death, galaxies across the age of the universe, the intergalactic medium that fills the cosmic web, the large-scale structure that organizes matter across hundreds of millions of light years. At every scale, Webb has found complexity. The planets are stranger than anticipated. The stars deviate from models. The galaxies formed faster and differently than simulations predicted. The cosmic web shows features that theories did not expect. This complexity is humbling. We thought we understood more than we did. Our models captured the broad strokes but missed the fine details. When confronted with precision observations, the models need revision. The revision is underway. Theorists are adjusting parameters, adding physics, building more sophisticated simulations. Observers are planning follow-up campaigns to confirm or refute the anomalies. The scientific community is doing what it does, testing ideas against reality and adapting when reality wins. Reality always wins eventually. That is what science is for. Webb has given us a clearer view of reality than we have ever had before. The view is beautiful, intricate, and challenging. It rewards contemplation and resists easy summary. What does the universe look like through Webb's eyes? It looks like a tapestry of light and shadow, structure and void, formation and destruction. Galaxies collide and merge, their stars scattered into intergalactic space. Stars form in collapsing clouds and die in explosive or quiet ends. Planets orbit in diverse architectures around diverse stars. Gas flows along cosmic web filaments, cycling through galaxies and back to intergalactic space. All of this is happening now, everywhere, continuously. The universe is not static. It is dynamic, evolving, changing on timescales from seconds to billions of years. Webb has frozen moments of this evolution in light. Each image is a snapshot, a single instant in a process that spans cosmic time. By collecting snapshots at different redshifts, we reconstruct the movie, understanding how the universe has changed from its earliest epochs to today. The movie is incomplete. We have frames missing, scenes unclear, transitions ambiguous. Webb has added frames, clarified scenes, illuminated transitions. But the full story remains elusive. Perhaps it always will. The universe is vast, ancient, and complex. Human understanding is limited by time, resources, and cognitive capacity. We will never know everything, but we will know more tomorrow than we know today, and more still the day after. This is the promise of science, the steady accumulation of knowledge, imperfect but improving. Webb is part of this accumulation. Its contribution is substantial. The science papers already published number in the thousands. The citations accumulate exponentially. The impact on astronomical understanding is measurable and growing. But Webb is not the end. It is a step, a large step, but still a step on a longer journey. What comes next? Other telescopes are operating now, complementing Webb's observations. Ground-based giants with adaptive optics that rival space-based resolution for some targets. Radio arrays that probe wavelengths Webb cannot see. X-ray satellites that detect high-energy phenomena invisible in the infrared. More telescopes are coming. The Nancy Grace Roman Space Telescope will survey wide areas at infrared wavelengths, providing context for Webb's deep, narrow observations. The Vera Rubin Observatory will map the optical sky repeatedly, catching transient phenomena as they occur. Future gravitational wave observatories will detect ripples in space-time from merging black holes and neutron stars. Together, these facilities will address questions that no single telescope can answer. They will connect observations across wavelengths, across the electromagnetic spectrum, across the gap between light and gravity. The questions Webb has raised will be addressed by this collective effort, not immediately, not completely, but progressively as observations accumulate and understanding deepens. The timeline is measured in decades. Some questions Webb has posed may not be answered in the professional lifetimes of the astronomers now working on them. The students who will solve these problems are perhaps now in elementary school, not yet aware that they will devote their careers to puzzles that Webb has defined. This is how science works. Problems raised by one generation are solved by the next. The heritage is passed forward, each generation building on what came before. Webb's heritage will be substantial. The questions it has raised are profound. The data it has collected is rich. The astronomers it has trained will lead the field for decades. Let us consider one more domain before we conclude: the search for life beyond Earth. Webb was not designed primarily as a life detection mission, but its capabilities bear on this most profound of questions. By characterizing exoplanet atmospheres, Webb can detect molecules that might indicate biological activity. Oxygen, in combination with methane, for instance, would be difficult to explain without life. The simultaneous presence of these gases, which react with each other, requires continuous production, perhaps by life. Webb has not detected such biosignatures. The planets it has characterized in detail are mostly hot gas giants, not likely abodes for life. The rocky planets around cooler stars that might be more hospitable have yielded mostly non-detections, no clear atmospheric signatures of any kind. This is not surprising. The search for biosignatures is extraordinarily difficult. The signals are weak. The interpretations are ambiguous. Even a positive detection would face years of scrutiny before being accepted. But Webb has advanced the search by demonstrating that exoplanet atmosphere characterization is possible. The techniques it has developed will be applied to better targets by future telescopes. The lessons it has learned will inform mission design for decades. The search for life is a long game. Webb has moved the ball forward. The goal remains distant. There is another way that Webb contributes to the life question: by revealing how common the conditions for life might be. The chemical elements necessary for life are produced in stars. The environments where life might arise require planets with liquid water and stable energy sources. The timescales for life to develop require planetary systems that persist for billions of years. Webb's observations constrain all of these factors. Its measurements of chemical abundances reveal how metals have accumulated over cosmic time. Its observations of protoplanetary disks reveal how planetary systems form. Its characterizations of exoplanet atmospheres reveal what conditions exist on other worlds. None of this tells us whether life exists elsewhere, but it tells us whether the conditions are common or rare. It informs our expectations, guides our search strategies, focuses our efforts. The conditions appear to be common. Metals are abundant. Planetary systems are ubiquitous. Potentially habitable worlds seem numerous. Whether life is common is a separate question. Common conditions do not guarantee common outcomes. The transition from chemistry to biology might be easy or hard. We cannot know without finding life, or failing to find it despite extensive search. The search continues. Webb contributes. The answer remains unknown. We have traveled far through the territory Webb has mapped, from the cosmic microwave background to exoplanet atmospheres, from the first galaxies to nearby stellar nurseries, from dark matter to molecular chemistry. At every stop, we have found puzzles, observations that do not match predictions, phenomena that lack explanation, questions that multiply faster than answers. This is the landscape of contemporary astronomy, a landscape of profound knowledge and profound ignorance intertwined. We know so much more than we did a century ago, and yet the mysteries have not diminished. They have multiplied. Each mystery is an invitation, an opportunity to learn something new, a doorway to understanding that did not exist before. Webb has opened many doorways. Some we have walked through, finding answers that satisfy. Others remain open, beckoning, promising discoveries that await future explorers. The exploration will continue. As long as curious humans exist, they will look up at the sky and wonder. They will build telescopes and launch missions and analyze data. They will argue about interpretations and test ideas against observations. This is what we do. This is who we are. A species that asks questions and seeks answers. A species that builds tools to extend its senses. A species that refuses to accept the limits of current knowledge as permanent. Webb is our tool for now. Others will follow. The questions will evolve as old ones are answered and new ones arise. The search for understanding will continue indefinitely. What did James Webb not tell us about the universe? It did not tell us everything. It never could. The universe is too large, too complex, too full of surprises. But it told us something important. It told us that the universe is stranger than we knew, that our models are imperfect. That discovery awaits at every scale and in every direction. This is not a discouraging message. It is the opposite. It means there is more to learn. It means the adventure is not over. It means the next generation of scientists will have meaningful problems to solve. The problems are hard. That is what makes them worthwhile. Easy problems do not advance understanding. Hard problems, carefully studied, yield insights that transform knowledge. Webb has given us hard problems. We should be grateful. The telescope continues its work. New observations accumulate daily. New discoveries emerge weekly. The scientific papers pile up, each adding a piece to an ever larger puzzle. The puzzle will never be complete, but it will become more detailed, more accurate, more revealing of the underlying reality. That is all we can ask. That is all we need. The universe is out there, vast and ancient and mysterious. Webb has brought us closer to understanding it. Closer, but not all the way. The journey continues. It always will.